Hi everyone and welcome back to Digital Design with Verilog course. So today we will discuss about the exercise 6 solutions which I gave you as homeworks. Also we will discuss about the topic why delays are not synthesizable. So I have mentioned in the course itself from the starting itself that delays are not synthesizable. So until now I hope you know what do we mean by synthesizable. Synthesizable basically means that you cannot, synthesizable means converting your code to hardware. That is what synthesis means. And why are delays not synthesizable, that we will understand with few examples, because this can get asked this can get asked in interview. Okay, so that's why this becomes a very important topic to discuss. Okay, so let's start first with the exercise 6 solutions. So this was the first question that I gave you as homeworks. So here what we have to discuss is basically we have like a full subtractor has three 1-bit inputs x, y and z, where z is the previous borrow, two 1-bit outputs. One is the difference, second is the borrow. The logic equations for d and b are as follows: x x complement y complement z, or x complement y complement z, and so on. And borrow logic is this: write the full Verilog description for full subtractor module including the IO ports. Remember that plus correspond to whatever logical operator. Instantiate the subtractor module inside a stimulus block and test all the 8 possible combinations. So this is basically a coding assignment only. So I have done this here. Okay, I have first made a full subtractor with the following logic equations. Now that I think of it, this will only work for 1 bit, right? If x, y and z are all 1 bit. If x, y and z are not 1 bit, then this will not work. So remember that x, y and z both have to be 1 bit. Okay, so I will write that on the code itself. Okay, so and this is the test cases, because they have asked us to design the test cases as well, write the test cases and test and check the print statement. So let's go back to the code and there I will show you. So if I just turn on the code, here I have the question 1. So in the question 1 we have this one. Okay, and this is the module, basically full subtractor module. So whatever they have told, that same logical uh, operation I'm doing. Okay, so although I'm like this is doing logical, this is doing logical bitwise OR. Okay, we're doing bitwise or they have told us to do logical operator. Okay, logical or operator, this on Dataflow. So either way works. Either you can do bitwise operator as well, you can do logical OR as well. Like it will provide you with a like 1 bit output only, either 0 or 1. Okay, so it doesn't matter, bitwise or logical OR, both are same in this case. Okay, so let's like this is the code and this is the test bench basically. So the monitor statements are here, so I have to write the monitor statements here, not here. This file should be empty. The monitor statements I will write here only. Okay, so the monitor statements are here. So let's of course first change our directory. So I will do cd, then I will go to my current project location. So this will be colon cd this, and I have got into my current project location. Now I will do iverilog. Okay, this will start something else. Iverilog, I have to do iverilog, then the vbp file. So this will be vbp, then the test bench verilog file. So this will be the test bench verilog file. I will press enter. Okay, some syntax error has happened in the in this file. Okay, something is wrong. What is the thing that is wrong? Here everything is correct, only this is correct. We're instantiating the module, and here this is also correct. Okay, okay, sorry, I messed up. We had to write dash o, right? I forgot to write dash o. So like remember, if you ever forget to write dash o, then it will throw up an error. So make sure to write the dash o. So yeah, I messed up there. Now if I do, yeah, okay. Now a lot of errors it is giving, invalid module instantiation. So am I doing okay? No, none of the module are getting instantiated here. Some end module is here. Okay, in line 15 is in the distance, lines 15 is here. Okay, I cannot write like this, right? It has to be inside a initial statement. So that is my mistake. It should be inside an initial statement. So why it should be inside an initial statement? Basically, right, these are mainly not used for synthesis. So generally whatever are not used for synthesis, they are written inside the initial statements because they run like sequentially. Okay, so yeah, initial, begin and end. So always, right, you do monitor statements, you're like without any assign statement. If you're assigning any value without assign statement, that needs to be inside the initial statement. It cannot be outside because this is reg, right? If you're assigning a value inside reg, so it has to be inside the initial statement. That is my mistake. So now if I start iVerilog, it will compile, no problems. Now if I do VVP and the file name, so the file name will be chapter 6 solutions VVP. Okay, so if you see, like, what output are we expecting? So what we are doing, basically we are subtracting y from x. So here 0 minus 0 will be 0 only, and borrow is also 0. So everything is 0 minus 0 minus 0 is 0 itself. So 0 minus 0 and borrow is 1. If borrow is 1, right, that means this x will become 2 here. Basically this x will become 1 here. Okay, sorry, this x will become 2 here. So basically it will be 2 minus 1, that is 1. Basically what do I mean by like borrow concept? So I will explain just in a second. Basically what you have to perform, you have to perform x minus y minus z. So your x, let's take examples, right? So like basically what here I am doing, I will explain later. Let's do in decimal number system. So let's say I am subtracting a number like this, 91 minus let's say 79. Okay, so what do? You cannot subtract like 9 from this one, right? What we do, we take a 1 from here, we take a borrow from the previous MSB. So if a borrow comes, this becomes 11. So 9 minus 11 minus 9 is 2. So I write here 2. Then it comes back here, right? So what happens? Then this becomes 8 because I have already taken a 1 here. It becomes 8. Like basically what we are doing, we are writing out 91 as 80 plus 11, so that I can subtract this 11 from this 9, so that I can get a proper number, and this 80 can then be subtracted from this 70. Okay, so ultimately this will be 1. So am I getting correct here? So 12 plus 89 is 12 plus 79. Okay, just hold on. 12 plus 79 will exactly give me 91. So I am absolutely correct. Okay, so I am absolutely correct. So that is what we do in decimal number system. Let's try to replicate the same thing in binary number system. So in binary, let's say I have this number, right? Let's say this is 1 0 and this is 0 1. So how do I subtract? So first I take this one here. If this one comes here, right, so this MSB is coming here. So once this one came here, its weightage in the next bit is its base. So this was decimal number system, it was 10. Here what is the base? Base is 2. So the weightage here will come as 2. So this will become 2 now. Okay, so 2, like basically this is 0 and this will become 2. So now if I simply subtract, I will be able to subtract 2 minus 1 is 1. So as I have taken a borrow here, so this will simply be cancelled to 0. This will be simply be cancelled to 0. So this will be 0. So this will be 0 1. Okay, so that's how you do the divisor. So here also same thing is happening, because x is 0, y is 0 and z is 1. So what is happening is I have to borrow a 1 from the MSB. So as I have to borrow, so the borrow bit becomes 1 in the question, in the result. If you see, the borrow here becomes 1. because it has to borrow from the next MSB. It won't be able to subtract on its own. Same for here as well. This will be like same for not for here. This is something wrong. It should be x minus. No, this is also correct. So I'm doing x minus y, right? So again, x is 0, y is 1. So again I have to borrow 1. So again divisor is like the result difference is 1. Why? Because as I have to borrow a 1 from the x from the MSB, so this becomes x becomes 2. 2 minus 1 is 1. That's why the difference is 1, and the borrow bit is also high. Same for here as well. Again the your again I'm subtracting. Now I'm subtracting 2, right? X minus y minus z. So I'm subtracting in total 2. So even though I have already taken a borrow, it becomes x becomes 2. 2 minus 2 is 0. That's why the difference is 2 and borrow is again high. Again now this is simpler. 1 minus 0 minus 0. So difference will be 1 only, and I don't have to take any borrow because x is large now. Again it is 1 minus 0 minus 1. So 1 basically it boils down to 1 minus 1, that is difference is 0 and borrow is 0 again. Now if it is like x and y are 1, it will be 0 and borrow again. If everything is 1, it will be difference will be 1, because 1 minus 1 will be 0. Then again I have to subtract another 1. So my I will have a like again 2. 2 minus 1 will be 1, difference will be 1 and borrow will be 1. Okay, so that was the solution for the first question. Just I wanted to write here this equation. This equation will only work for 1-bit numbers. Okay, this will not work for higher bit numbers because all of these are bitwise operators. And of x can be something else, so just be careful about this. All these equations will work for 1-bit numbers. So that was the question 1. Let's now go back to our notes and check the question 2. So let me just comment this one out. So let me show you the question 2. So now this is done. So question 2, what is question 2 telling us? It is basically telling us to design a magnitude comparator. Okay, so this we have already kind of done, right? So a magnitude comparator checks if one number is greater than or equals to or less than another number. A 4-bit magnitude comparator takes two 4-bit numbers a and b as input. We write bits a and b as follows. The leftmost bit is the most significant bit. So a is this and your b is this. The magnitude can be compared by comparing the numbers bit by bit. Okay, so this we have already done, right? The greater than or equals to operator we have already programmed. That is what they are asking us to find out. So they have already given the like relation to find out the magnitude. So to realize this functionality, let us define an intermediate variable. Notice that the function is x0 function. So x0 basically checks if two bits are equal or not. The three outputs of the magnitude comparator, a greater than b, a less than b, a equals to b, they are defined with logic equations. This I have already derived, right? In our previous lecture I have already derived, not in the previous lecture, to previous lecture already I have derived these equations. So now it would seem like a piece of like cakewalk, right? It would seem like a cakewalk because all this we have learned already previously. Write the Verilog description of the module magnitude comparator. Instantiate the magnitude comparator inside the stimulus module and try out a few combinations. So this is our task. So we will try to do this. We have already done this. So this is the code basically. If you see, as we are comparing bit by bit, so all this will totally be correct because I am comparing bit by bit. So all these equations will be totally valid. So I have already explained basically the logic behind taking all these equations, right? These already have been explained. So I don't think I have to explain you this logic again. So this is the code basically. This is the stimulus model. I have to first get the monitor statements for question 2. So again I have to write like initial begin statement. So I hope you remember the equations, right? What we derived in the previous lecture. I hope you remember all this. Initial begin and okay, and here if I start, this is fine, let me start from here. So this is the magnitude comparator basically. Here a greater than b, a less than b, a equals to b, all these things are there. So these are intermediate variables. Basically this checks the equality of those individual bits. This equation I have already explained. First I do a and b, right? B complement. Now if this is false, then I come to the next statement. First I check if they're not equal, then only proceed. If they're equal, then don't proceed. Okay, don't proceed. That is what it means. This have been derived in the previous lecture. So I am not explaining you the equation. I have just directly coded it. Okay. So now let us run the code and check whether whatever we have coded is correct or not. So I will do iVerilog, I will do VBP. Let's see. So first at time 0 my A is 1010, B is 101. So what am I expecting? I am expecting that my A to be greater than B. Why? Because the first two bits are same, but this bit is higher than the third bit of B, right? So of course A will be greater than B, which is correct. A greater than B is high, it is 1. So only when A will be greater than B, then only this will be high. If A is less than B, then this will be high. If A is equal to B, this will be high, else all of them will be 0. So the others are 0. Here if I see again, the first two bits are same, but this time the third bit of B is higher. So A less than B is high, all others are 0. Here if I see the all both of them are equal, A is equals to B. So this is A equals to B is high, the others are 0. Again here A is equals to 0 1 1 0, B is equals to 1 1 1 0. So again what do I see? B is greater than A, correct, because the MSB of B is higher than the LSB, MSB of A. So that means A has to be less than B, which is the option part B, right? So A less than B is the high. So I hope you have understood, like we have checked all the test cases. You can play around with this, okay, and test it for yourself. So this was the question 2, pretty simple because we have already learned the logic equations in the initial lectures of operators, correct? So now let's discuss about question 3. So if I come to question 3, basically we have to design a synchronous counter using master slave JK flip-flops. So don't worry about the internal workings. I hope you have understood the internal workings in the digital electronics course. Here, even if you have having few doubts, right? How what type of things will code. If you are having the doubt, don't worry about it. That will be sorted out in the behavioral modeling. Okay, there will code more of these flip-flops in the behavioral modeling. So if you have some doubts while understanding the code, stay assured we will clear it in the behavioral modeling. Okay, so mainly what they are telling that our we will have a active low clear signal. Basically if the clear signal is low, then all of the flip-flops will be cleared basically. uh, Data on the negative edge, we will receive data. Data gets latched on the positive edge of the clock, and the output of the flip-flop appears on the negative edge of the clock. Output of the flip-flop gets uh, latch on the gets appeared on the negative edge of the clock. So flip-flop output will be on the negative edge, data will get latched on the positive edge. Counting is disabled when count enable is low. Okay, counting will be disabled. So if this signal is low, then there will not be any counting. So all of this will be 0. Then if this is 0, right, automatically this is also 0. If this is 0, then automatically this is also 0. So that is how the counting works. So before starting like the code, I wanted to explain one thing, that here, right, this circuit diagram is wrong. Okay, I was like doing the code, and then once I had done the code, I got to know that this circuit diagram is actually wrong. How the correct circuit diagram will be? Basically the correct circuit diagram will be, you have to remove this. Okay, I will copy this and then paste this over here, and basically, right, your correct circuit diagram will be, this will be removed, this will not be here actually, this wire should be here. And same for the previous ones as well. So that was incorrect actually. You had to, for the correct toggling, right, you have to take the previous Q outputs, not the present Q outputs. That is where there was a bit of printing mistake in the book. So this were all correct. Okay, to enable the count enable signal. So what we will do, we'll just simply use NAND gates here, and we will, after making this JK flip-flop, then we will just simply make this AND gates connections. That's what we will do, right? In data flow level of modeling, that is what we do. So here I will show you. So this is my test bench basically, like the signals, output signals are there, count enamels, all these things are there. Don't worry, the code will be provided. Also, I have done a test bench for the JK flip-flop as well. So if you want to test the JK flip-flop, you can do that separately. It is a separate test bench. But for now, let's discuss about the synchronous counter. Okay, so this synchronous counter, like as I mentioned, like this T0 is just the intermediate signal. What is this T0? T0 is all of this, right? This one, this is my T0, this is my T1, this is my T2, this is my T3. Okay, that is it basically. These are my intermediate signals. So these are connected through AND gates and count enable. So the first one is directly equals to count enable. The second one is AND of T0, that is count enable, and Q0. Okay, so that is what is written over here. Same thing, and I'm giving the JK flip flop these as my inputs, right? T0, like here, if you see, the first flip flop is receiving always T0, right? J and K both are T0. The second flip flop has J and K as T1. The third flip flop has J and K as T2, and the fourth one has J and K as T3. So exactly that is what I am doing. And clock and clear are just the same signal only. It is connected parallelly. So here if I see, clock and clear are connected parallelly. Okay, no problems with that. So I hope you have understood this part and logic. This JK flip flop, just whatever the gates are written, that those things I have implemented here. Just try to be careful here with the intermediate signals. If you even miss one signal, your output will be totally high impedance or X. Okay, so just be careful while writing all this expression. Try to tally this, double check this once. Okay, once you derive this, be careful. That's why I'm just mentioning, this is not that difficult. Just see the circuit diagram and implement the gates. That's it. That is what you have to do. See the circuit diagram and implement the gates. So like I will just show you one example. Let's say take this example, right? The first NAND gate. So if I just like somehow if I will be able to show both, it will be difficult. So here, right, if I go to the first NAND gate, you see the output of the first NAND gate, like this is my first NAND gate. Output is A, input is J, clock, clear, and Q bar. J, clock, clear, and Q bar. So if you see here, the input is like this is the output, right? Input is J, clock, clear, and Q bar. What is the output? Output is A. Similarly, for the other NAND gates, you can do the same. This NOT gate is the bar of clock. Okay. So now if I just compile and run this code, I Verilog, of course, you like I am in the same project directory. If I just run this code VVB, it will work as a counter. So now if I just show you the waveform, because this counter, right, counters, we will understand this best with a waveform. So this chapter 6 module, then Q, I will directly plot the Q and the clock and the count level and the clear. Okay, so clear, right, is always active high. So see, you see, until when the clear is low, it always is basically low. The output Q is always low. Here, right, once the count enabled, then after this, the falling edge of the clock, then we start with our count. So this becomes 1, 2, 3. Then here again, my count enable is 0. If my count enable is 0, that means I will stop my counting, right? I will not count. Again, my count enable has turned high here, but obviously I will wait for a low edge, right? This is my low edge. So once I receive a low edge, then only my count again starts. It resumes, right? It does not restart, it resumes. So just be careful about that. Then again it starts from 0, 1, 2, 3, 4. So just one more thing I wanted to see, that what if I make it clear 1? Okay, here, right, once I do re-enable the counting again after a delay of 50, if I make the clear low, because it is active low clear, so if I make the clear low, then it should again reset. So that is what I also wanted to see the behavior. So let me do the VVP, then do the GTK wave. So if I now do the GTK wave, if I just see this count 11, clock, and clear. So if you see, once the clear is there, right, it automatically directly clears to 0. it does not go to some f or something, it directly clears to 0. If the clear is low, then it will always be 0. Okay, it will always be 0. So yeah, that is what we wanted to see, and I hope you have seen this. So I can do this after a delay of at least 150, because at least I want to count till certain position. So let me just rerun this again. So this will be, so you can see, right, here it is 8 and then again it resets. So I hope you understood like the whatever I wanted to explain, this counter thing. So that was about it for the like exercise solutions. Now I will discuss about a topic on why delays are not synthesizable in real hardware. In Verilog, like this hash 5 are used for simulation purpose to see the delays, but these are actually not synthesizable. When a synthesis tool encounters a delay statement, it simply ignores it. It will simply ignore it. What does this delay statement actually means? So y here will be, y will be ready at 0 nanoseconds, but it will be assigned, but will be assigned at 5 nanoseconds. Okay, it will be assigned at 5 nanoseconds after a delay of 5 nanoseconds in the simulator. But in the synthesizer, while we will convert this into hardware, this will not come into effect. Okay, so in synthesizer, this delay will simply be ignored, and the assignments will happen immediately without any temporal effect in the real hardware. Now, why is that the case? So let's understand why is that the case. So first one is, when designing real hardware, delays must be implemented using actual physical resources such as lookup tables and registers. So it is not that simple to simulate or the delays. Let's say you want a 5 nanoseconds of delay. It is not that simple. How do you simulate the delay? With the hardware components itself, like the memory elements and registers. So let's say, for example, in an FPGA, delay element must be constructed using the available resources, but their timing can be influenced by many things. So let's say you want to synthesize a delay with an AND gate or something. Okay, just giving you a basic example with an AND gate. Okay, now actually the delays, right, are not constant. It varies. Like let's say this AND gate has a delay of 5 nanoseconds. So you try to simulate, like you try to implement this hardware for simulating the 5 nanosecond delay. Okay, so AND gate, right, AND gate will have some problem. It can vary with the process variations. What do I mean by process variations? Process variations is how this AND gate was made. This AND gate was made with CMOS technology, right? Now, while making the CMOS technology, something can go wrong, right? Not wrong, basically, there can be process variations. So if you know a bit about VLSI, you will know that our chips, right, are made in factories. So they are made in certain conditions, like they have this kind of big wafer, and in the wafer our chips are made. Okay, if you know a bit, if you don't know, you can ignore this, just take my word. My word is that when we are designing, making these chips, right, all the small transistors, they are just bit different. Okay, although their characteristics is almost similar, that I have explained in the first lecture, lecture 0, that they will be almost similar, but there can be a bit of different. Let's say this AND gate is made here and one AND gate is made here, there will be slight process difference. Like let's say two people are twins, so even though they are twins, still there will be some difference between them, right? Exactly, that is happening over here. So even though they are made with the exact procedure, there will be some difference. Due to that difference, this AND gate 1 may have 5.001 nanosecond of delay, and this AND gate might have 4.9 nanosecond of delay. Okay, just I'm telling you, I'm exaggerating it, but it will not be that much of a difference, but the difference will be noticeable. So if there is a difference, right, and once we try to model with the hardware components with the delays, we will not be able to exactly model. Why? Because as I explained, the process variations, how they are made, Due to that, the different AND gates will have different delays. If the temperature changes, then also how each AND gate will react, that also will vary. Obviously, not very largely, they will be almost similar, the variation almost will be similar, but they will be not exactly similar. That is the problem. And if voltage changes, any high low voltage changes, then also how they will behave, we don't know. Due to all this, right, it is very difficult. It is fine, okay, you will say I can easily design a 5 nanosecond delay. Okay, no problem, design a 5 nanosecond delay. Let's say I want a 500 millisecond delay. How will you design a 500 millisecond delay? How many AND gates you will require? 1000 AND gates you will require. Not 1000, sorry, not even 1000. So 1000 means 5 milliseconds, not even 5 milliseconds, sorry. 1000 actually means 5 microseconds. Then I have to go to milli. So like this will be too high, right? Too high. So basically this is 5 into 10 raised to power 9. I have to go to 5 into 10 raised to power minus 1. I have to go to 5 into 10 raised to power minus 1. So I have to, how many AND gates I will require? 10 raised to power 8. I will require 10 raised to power 8 because this is how much of a delay in seconds. This is 5 into 10 square into 10 raised to power minus 3, that is 10 raised to power minus 1. So I will need these many AND gates to design a delay of 500 milliseconds. That will take up too much of our chip resources, because if you know, we have a specific area, right? If you know your smartphone, you have your smartphone, right? So your smartphone has the processor just here, like inside, if I show you, just somewhere here, okay? And the space it takes is this one. Okay, in the lecture 0 as well, if you see how small the chips are, like you have, like obviously you want everything on your hand, right? In this small hand you want to access everything. So to develop that technology, we cannot take too much of space. Now to develop a delay of 500 milliseconds, I have to use 10 raised to power 8 NAND gates. Can you imagine how much wasted space that will be, how much wasted hardware resource that will be? So of course that is not feasible. Okay, that is not feasible, consuming excessive cheap resources, and it is not feasible for us to use. So that is why we don't use it. Okay, first constraint is this process variation, voltage fluctuation. Second constraint is excessive resource utilization, as explained just in a second, right, as I have explained just now. So we cannot use these, like to design 500 milliseconds, we cannot use all our hardwares in those cases where it is a application specific IC, right? What is ASIC? ASIC is an application specific IC. So I am designing for a specific application, and if I take like 70% of my available silicon area with for designing this delay only, so what will I be left with? I will not be left with anything. So that's why in ASICs, right, while I have limited power, limited area, okay, limited hardware, I will not be able to design these kind of delays. Next is in real world, how will we design the delays? In real world, we rely on synchronous design principles, where timing is determined by the clock signal instead of arbitrary delays. Okay, so like we can design our delays using clock signals. There are other ways which designers use, such as counters and FSMs, to introduce delays in terms of clock cycles. So we can introduce delays in terms of clock cycles. That is what we can do. That obviously we will not cover in this lecture, but in real world, that is what we can do. So if in the interview you get asked, you will give the reason as these two reasons, right? This is why we don't generally synthesize the delay. These two are the reasons, and the approach is this one. We follow this approach in real life. Okay, few more things are written here. So like for if you need a 200 microsecond delay in a system, so what you will do with a 5 megahertz clock, you can use a counter that can count up to 1000 cycles rather than using the delay statement as hash 200. Okay, so here I have done the same thing only. Basically, like if you don't understand the code, don't worry, this if else this will be taught in the next like in the behavioral modeling. So this if else is very basic thing. So if like I will keep on increasing my counter value, counter will count till 25,000 delays, and then once this counter counts till 25,000 delays, then I will stop. Okay, then I will do something after it like gives this much of a delay, right? So yeah, I hope you have understood how we can implement the delays in the real hardware. Like you can go through this. So that was about it for this lecture. I hope you have enjoyed this lecture, and trust me, like we whatever we have learned, right, we have learned everything very from basics and fundamental. So that's why we were able to correct this circuit diagram as well. Okay, so I was not able to find the solution anywhere. Like this is a very famous book, but I was not able to find the solution anywhere. So yeah, I hope you have understood the like concepts whatever we have learned. I hope you have understood the gate level modeling. So this is the end of module 1, and if you have reached until this far, make sure to comment on down on the video that I have reached the end of module 1. Okay, and of course you can say if you felt the content was good, you can say if you felt the content was bad, you can also say that there is no like foundation. Just if you have felt the content is good, make sure to comment on the first video of this lecture series, so that other students can join in. Okay, so will the next module be continued or not, that is a surprise that we'll see according to your response. Thank you for watching, and I will see you in the next lecture.